a relation between the time it takes to repair n number of computer units. So for example, this data would say, the first row so would say that it took about 23 minutes to repair 1 unit of data. So this time would include the time taken by the repair person to come, like to start his car from the repair shop to till the time he reaches your home and finish repairing your computer. That would be the entire time. So it would take 29 minutes to repair 2 units of computer, 64 minutes to repair 4 units in one instance, and 74 minutes to repair 4 units in, let's say, some other instance. So the idea. Okay, so what we're going to do is that we are first going to import all the necessary libraries. So I'm going to say import, let me zoom in a bit. We'll say import numpy. So numpy as np. Now what is numpy? Numpy and these pandas numpy are certain libraries that we import. Now the reason we use Python is because, and not C++, is because there are lots of data science oriented libraries already written. So that you don't have to write the code from scratch. You can simply import the library and start using it, because your main concern is with machine learning and data analysis. You are not, like, data scientists are not inherently developers. But in C++, if you have to write a certain program, it will take lots and lots of line of code. But in Python, Python inherently is is very redundant. When I say it's not redundant, like, it's like it first of all requires very short amount of short lines of code to do the same task in C++. B, there are lots of libraries pre-written and predetermined to do some data science work. So such libraries are NumPy and Pandas and Matplotlib. So I would say import Pandas as PD. And what is as PD? I'm giving them as alias. It's a short form. Like, I don't want to write NumPy and Pandas again. So I will, instead of calling NumPy, I will call it as NP, short form. That's it. Similarly, I would say import a certain library called known as Matplotlib.pyplot as PLT. This is used for visualization. And then I will write Matplotlib. Anytime you have any computer, you can always ask me. Okay? And then I will execute this thing. So to execute, either I will run, click on this button run, or I will say I will click Shift plus Enter or Control plus Enter. So I'm going to use the shortcut Shift plus Enter. It is running in the background. Okay, now it has run. Now I want any and all kinds of warnings to be ignored. So I will say import warnings. So this is optional, by the way. So I'm just using it so that it is so that any warning doesn't come. So I'll say warnings dot filter warnings. I'll execute this. Okay, it's done. Now I will go and create a data frame to build the regression model. So first I will have to read the data set. As you can see, the data set is in the format is in a CSV format, comma separated values. There are several kinds of formats that we can have: .html, .json, .csv, .xlsx. So xlsx is Excel file, or you can also read XML files as well. So here we are going to read CSV file. So to read the CSV file, I will say pd pandas.read CSV function underscore CSV, and I will, inside the commas, I will have to give the path. Now it is, since it is stored over here inside this local repository, so I'll simply say where is it? Computers. This one, computers.csv. So I will write, I want you to read computers.csv file, and I will store this inside a variable known as computer, and it's actually an object. Okay, so I will do this thing, and if I were to present the first 5, let's say computers, if I were to read the first 5 tables, so first 5 rows of the this data frame, I will say computers.head and I will execute this thing. So it will print out the first 5 lines. So as you can see, there are 5 rows and 2 columns, units and minutes. Now this 0, 1, 2, 3 written in bold is not column, it is an index. Index is like to access a certain data inside the data frame. This is known as a data frame. Data frame is nothing but the pandas version of table, that's it. Okay, so to access the units like this 2 which is stored inside the units column, so I will say fetch me the data in the units column in the at index number 1. Simple as that. So these indices are used as the S number, serial numbers in some sense, you can say that. Okay, so let's do some feature engineering over here. So now this is the part known as data engineering. So this is the part of feature engineering I was talking about, data engineering. Now I may miss some comments, so you may have some comments over here, so it doesn't pop up in my feed. So anytime you have any doubt, please unmute yourself and speak up. Okay, it is fine to speak up. Okay, so here you are to learn, and if you have any problem, any trouble, I don't want to miss the chat, so you can always speak up. Feature engineering, so it will looks like let's say if I want to find the mean, I will create a variable known as mean value, and to find the mean I will say, so let's say if you want to find the mean of the minutes, so what is the mean value of all the minutes? So 23 plus 29 so on till all the last value divided by 14. So instead of doing that, I will simply call I will say in the computers data frame. Okay, so first let me say, if I were to say computers and if I were to call minutes, it will fetch me all the minutes value over here like this thing. Make sense? So it's 23, 29 all the way to the last one. So to find the mean value, I will simply say dot mean. Okay, and it will fetch me the mean value, and I will store this mean value inside a variable known as mean value, mean underscore value. Okay, it has been stored. And if you want to print the mean value, you will say print mean value. Now, to plot the graph you will have to use the method known as Matplotlib. You'll have to use this particular library, and I will, since I have imported this pyplot as PLT, I will use that. To do that, it's pretty simple. I will say to plot the actual time taken for various values of number of faulty units. So here basically we are trying to create a scatter plot. So to identify the scatter plot, I'll say plt.scatter function, and here I will give the x and y value. So in our case, the x value, let's say, so what happens in a scatter plot? So scatter plot looks something like this thing. Let me tell you very clearly. So if that two values like this thing, so these are some scatter plot. Okay, and if this is the x value and this is the y value, scatter plots are used to find the relationship between x and y values. So in this case, you could say that x is directly proportional to y, or in other words, as x is increasing, y is also increasing. Okay, so I'll simply say, so I'll go over here and I'll say x is equal to, let's say, computers units. So here you want to find the relationship between units variable and minutes variable. Okay, and similarly I will say y is equal to computers minutes. Okay. And here I will feed in the value x and y, and I will say color. You understand what I mean by color, blue, and I want the marker to be, hang on, this should be in inverted commas. Okay, and if I were to plot this thing, it will look something like this. So this is the idea behind this thing. So as you can see, x and y axes are mentioned over here like this thing. Now, obviously, what is this x axis and y axis? It's not mentioned. So I want to mention, like I want to label them as well. So to do that, I will say, so I will add some annotations, and I want to draw a line of mean from where the mean value passes. So I will do that as well. So I'll say to plot the mean value, plotting the mean. I will say plt dot axis horizontal line h line ax h line, where y is equal to mean value that I've stored before, and color is equal to let's say red. And then I will add some annotation, adding the annotations x label and the y label. This will look something like plt dot annotate. I'll say mean repair time, comma, the xy value should be around, let's say 7.5, comma, mean value plus 2. Okay, and then I will set plt dot x label to be units, and plt dot y label to be, let's say, minutes. If I were to show this thing, this will look something like this. So let me explain what I really mean by this thing. Okay, so this horizontal line is used to, this particular line of code is used to draw this line over here, to draw the horizontal x line. So this means axis horizontal line, and I want the color to be red. And the value where it will be drawn will be at y is equal to the mean value. That was y is equal to 97.21. So as you can see, it is very close to 100. That's fine. And then I'm using annotate function to annotate this thing, to add this mean repair time. And I want to give the coordinates from where this would be written. So I gave the coordinate, the x coordinate to be 7.7, and the y coordinate to be mean value plus 2. Now, if I hadn't given this mean value plus 2, it would have been written on top of the line itself. And we don't want that. We want it to be written a bit above the mean value. So that's why I said mean plus 2. If you were to give mean plus 10, it will write over like way above that. So that's why I want to give an appropriate value. So I'm giving appropriate coordinates for x and y over here. And so you could give 7.7 or 7.5, whatever it is over here. Now this is the idea. Now, since so here in this case, there is only one predictor variable, and only like for the target variable. Now, usually the target variable is only going to be 1. You will only use one target, like you'll have to only predict one thing, but you can have multiple predictor values. So in this case, I'm giving an example of a simple linear regression. So I will say that there's only one predictor variable. So if you were to, so since we only have one predictor, we are going to build a simple linear model, so that our model will contain a single independent variable. So unit is the independent variable, usually x, and minutes, that is y, is the target or the dependent variable. So here, the model is going to be a simple straight line with equation y is equal to mx plus c. Now, if you recall, from your mathematics session, the equation of any line, equation of a line is defined as like this thing: y is equal to mx plus c. What this means is that where m is the slope and your c is the intercept. Now, if you don't remember this thing, let me explain to you. If there is a line such as this is the line, this is the line, and let's say this is the line over here. Okay, the angle that it makes, the tangent of this angle will be the slope. So the slope will be, so this is the slope, by the way, will be equal to the tangent of that angle. The tangent of the angle that the line makes with x-axis, and the intercept will be the place at which the line cuts the y-axis. So intercept will be c, the intercept will be the place where it cuts it. So that would be 0, c. The coordinates will be 0, c over here. So this will cut over here, Okay. This is the general idea. So what that means is that every single line that you see in a 2D space, every single straight line that you see in a 2D space, its shape, well, frankly speaking, the shape will be straight line, but its characteristics will be determined by slope and the intercept. So these are things that you will actually use it. So I will use the slope and the intercept. So if I were to give you a value such as this thing, so if I were to tell you that there is a line over here and the line is passing at, let's say the line is something like this thing, and let's say this is the value at 97.2. In other words, the coordinates are 0, 97.2. So can you guess the slope of, so can you guess the equation of this line? Anyone in the comment section? Let me see. Anyone? Exactly, y is equal to 97.2. Why? Because it is cutting that. In other words, what you can see over here is that it is, so when I say y, so its equation would be something like y is equal to, so the general equation y is equal to mx plus c. Since it is parallel to x-axis, m will become 0, and c is basically the intercept where it is cutting, and that is 97.2. Since m is equal to 0, this will become y is equal to 0x plus 97.2, or y is equal to 97.2. This is the general idea. Okay, perfect. So coming back to our equation, so I will create 3 simple lines. Okay, so I will, what I'll do is that I want to create a random, like this is the idea, right? So this is my model over here. So if I were to create 2 lines, something like, let's say something like this thing, this is, let's say, line number 2, this is line number, sorry, this is, let's say, line number 1, this is line number 0, and let's say there's another model like this thing, line 3, sorry, line 2, sorry, line 2. So this will have an equation. This will be y is equal to 97.2. Okay, this will be y is equal to m1 x plus c1, and this will be y is equal to m2 x plus c2. In other words, I have to find the appropriate value of the slope and the intercept to determine which line would be this one. Okay, so there are a couple of ways. I can either use calculus, or either I can use fill. To find the best fit line, we will use the calculus. So before doing that, let's try some random variables. We will hit and trial. We'll do hit and trial method, and we'll see if we can come up with a like, can we come close enough. So I will give the model number 0. This is known as, this mean one will be the model number 0. So it will be like this thing. I will say model. Let's say model 0 is equal to computers mean, sorry, computers, or let's say we already have that, right? So we'll say model 0 is equal to mean value. Okay, in other words, this will be model 0 would tell me the estimated time is equal to the mean of all the minutes. Okay. Similarly, model 1 is equal to 10 plus, or let me say this thing, 12 into computers units plus 10. This is like saying y is equal to m1 x plus c1. Okay, everything. Similarly, let me copy this part, and I'll copy this over here. Model 2 will be, I'm giving some random variable. Now instead of 12, you could have given anything. So here I'm giving some random variable known as 18, and here I'll say 6. Okay, and this will be like y is equal to m2x plus c2. Okay, And so the outcome of these models are added to the data frame for visualization. So I will create an extra column over here. So here, as you can see, there are only 2 columns. I will add extra columns. So to do that, it's pretty simple. I'll say computers, the name of the model. So I will say model 0 is equal to model 0. So I'll just copy this part. Okay. And here model 1 will be equal to model 1, model 2, and this will be equal to model 2. And if I were to print the first 5 values, computers.head, it will look something like this thing. So that means I've added an extra 3 columns over here with certain values. So how would this look like? So to do that, it's pretty simple. I will type the appropriate code. I will create a canvas board or a figure and an axis to do that. So I will say dot subplot, and then I will use the plotting part. So I will say plotting the actual minutes. So I'll say ax.scatter. I want to do the scatter plot. So I will say x is equal to units, y is equal to minutes, and here data, I'm giving the data is computers, and the label to be actual repair time. Okay. To plot, I will to plotting model 0 predictions ax.plot computers unit. So this is the x value, and the y value would be computers model, this one, model 0. So it should be capital M, model 0. Color is equal to red, and your label should be equal to model 0. Okay, I'll just copy this the same thing over here. And hang on, I will just change these things. Green, and I'm labeling as model 1. So model 1 will be green in color, and model 2 will be, let's say, black in color. This is model 2. And since I want to plot them, I will say ax dot set y label underscore y label. I will say the y label will be named as minutes. Ax dot set, oh, it should be set underscore x label. I will say units. Ax dot set title. Some, I will say, speculated models, because I'm using some random models over here, and I will add the legend as well. I'll say legend, and that's it. Okay, there is a problem over here. Oh, okay. Yeah, I'm sorry. This should be. I should remove this part. This is what's gonna happen. So if I were to just let's say color is equal to this looks better. So what happened? This was the code that I was writing. So this X label will actually is used to write the label over here, and same goes for y label as well. So x label is mentioned as units, and y label is mentioned as minutes over here. So these are three models in front of me. So I could say that definitely black and green looks a better fitting model than the model number 0, that is a red model. But again, the question arises, which one is better between black and green? We don't know. Like, it looks like both of them are pretty good, but empirically speaking, which one to find? So here we are going to use something known as the regression model. So to find the best fit model, we will use something known as the error methods. So we will first calculate the error, and we will choose that model which contains the least number of error. So for example, let me tell you what an error is. So error is nothing but, let me change the color. Error is nothing but the difference between your predicted value and the actual value. Okay, in other words, how off you're from the actual value. In other words, let's say this is your graph, and this is your data point, like this thing. Okay, and this is your model that you've done. So at this particular point, at let's say xi, this is the actual data point, and your predicted, and let's say this is the actual one. So I will say the actual one will be yi. So yi will be, let's say, actual value, and your predicted value would be, let's say, yi hat value is equal to predicted value. So your error would be equal to, it's pretty simple, will be equal to y hat I minus yi. It's fine. Okay, and in this case, we will say, we can see that since y hat I is greater than yi, this will be positive. Okay, however, if the data point would have been here, or if the model was somewhere over here, or in other words, if the data point would have been over here, relatively speaking, the error would have been negative in nature. So basically, what is error? Error is like how off you are from the actual value. So this distance over here that you can see, so the distance that you can see in the yellow line over here will be, this distance will be the error values. So if there is a point, like this thing over here, and this is, let's say, at xj, so error at this point will be, so let me change the color once again. Error at this point will be this point. So this would be error 2, this will be error 1. So this is error 1. So your error 2 will be termed as, so obviously at xj also there will be, this will be yj, and the predicted value will be over here, y hat j. So it's a bit of mathematics involved. So your error 2 will be equal to the difference between y hat j and yj. And this will be negative, because as you can see, yj is greater than y hat j. That is why this part will be negative. This is the greater, and this part will be smaller, and smaller minus negative will yield you a negative value. And to find a model, to find the best fit model, you will find the total sum. So the total sum will be, let me change the color once again. So total sum will be total sum of errors will be E1 plus E2 plus all the way till all the values till En. So if there are, let's say, multiple points like 1, 2, 3, 4, 5, 6, you will take all the error values over here and you will sum them up. And this will be mentioned something as summation of E, I, and I all the way from 1 till N. Now the problem with total sum of errors would be all the positive values will cancel out all the negative values, as you can see. Like if there is a point over here, this value will cancel out all the over here. So your total sum of errors will be very, very close to 0 at the end, and you don't want that. So one solution would be, you know what? You square all the values and then you take the sum, so that negative values will also become positive. So that is why in regression, to find the errors are usually, instead of saying like take the sum of all the errors, instead of saying something like EI, instead of doing this thing, we will square them. Okay, this is known as sum of all the errors. So sum of all the squared errors. Okay, so I will say squared errors or something like this thing. I hope you got the idea why I'm using the squared errors, so that I can negate the effect of positive cancelling out the negative ones. So I will do that right now. So before we do, so let me give you a demonstration how we will do that. So let's say let's first validating model 0. So I will say model, I will create a new data frame known as model 0 observation is equal to pd.dataframe, and I will create a dictionary. I will say units, computers, units, actual time, I'll take computers. So bear with me a minute, please. Predicted time. Model 0. Here it should be, I'm creating a new column known as basically computers, model 0 minus computers minutes. And I will print the value. As you can see, I'm finding the difference. So this was to repair 1 unit at a time. It took, for according to model number 0, that is this one, red line. Okay, so according to this thing, the actual time it took was 23 minutes, but a predicted time is about 97.21 minutes for the first one, which is definitely wrong. So the first one, as you can see, the error will be calculated like this thing. So this is the first error that you're getting. So this was about 23. This was 23, and this is predicting 97.2. Same thing happens for everyone. So as you can see, all these values are canceling out the negative values. So if you consider all these values, all these lines below the red line as positive, then relatively speaking, all the values above the red lines will be considered negative. And that is what I've shown over you over here. I want you to focus over here. Look at this thing. All the values after this thing is coming out to be negative, and all the values after let's say index, so before index number 7 are positive. So if you were to find the errors, how would you do that? Just take the sum of this column. So in Python we have a function known as sum of the errors. So sum of errors will look like, so take the sum of model observation of errors. The error. It will give you 1.42 into 10 to the power minus 14, which is extremely close to 0. To avoid that, we will take the sum of squared errors. So let's say sum of squared errors. So what to do? It's pretty simple. Take the square. Yeah. So I'll say model 0 observation. Take the error and do the square. So this is the way to write this, to take a square of a number in Python. So it turns out to be around 27,768. Similarly, the way I validated the model number 0, I will validate model 1 as well. So I will just replace all these values. I will say minute. I will say model 1. Okay, and it will look something like this thing. So as you can see, the errors are something like, and the sum of I will only be bothered with sum of square errors now. Now that I've established sum of square errors is not in our interest. So I'll say the sum of square errors for model number 1 would be around let's see, 4,993. So clearly its error is lower than this error. Same will go for validating the model number 2. So let me copy this part. So validate model number 2. And to find the sum of square errors, model number 2 would be 5,001. So clearly, empirically speaking, our model number 1 is better than model number 2 and model number 0, clearly. Okay. However, this is not the best fit model. In other words, this line over here, this green line is better than black and red one. But is this the best that we can do? Turns out no. We can use calculus to find the best value. Now, to avoid all the mathematic congestion and everything, I can do that. I have no trouble in deriving how we came to the formula, but it will take a lot of time, and the equation is sitting just next to me right now. However, to avoid this thing, like if let's say if you don't have the calculus background, this and that, you can find that thing you simply have to, like, to avoid the calculus, you simply have to import a library. And how to import the library? It's pretty simple. So to import the library, it will look something like so first let me tell you how to do the calculus. So, okay, after doing all the necessary calculus, you would have something like this thing. So I've already mentioned this thing, and I will just copy paste it. Okay, I've already written the code before, and if you were to do the calculus, you will come with certain equations and some appropriate value of x and y. And you will do that, and after doing calculus, you will find such values of intercept and coefficient where the sum of square error is going to be the minimum. Okay, so you will differentiate sum of square errors with respect to intercept and the slope. And when you do that, you will come up with these equations. You can ignore this thing right now. And when you do that, it turns out the intercept's appropriate value is 4.16, and the coefficient, or in other words, in this case, the slope will be 15.50. That means at slope 15.50 and the intercept 4.16, you will get the least errors. So if you were to visualize that thing, this will be the best fit model. And as you can see, this is cutting through the our data set perfectly. And if you were to validate this best fit model, the sum of squared errors will come out to be around 348.84. Now, what if you don't know all these calculus and you want to do this thing? It's pretty simple. You can come up with the same equation, same value of intercept and everything, by using the simple linear regression class in the library from the sklearn library. So to do that, you'll say from sklearn. So sklearn is scikit-learn. It's a special library to do machine learning in data science. So you will say import sklearn.linear model, import linear regression. Okay, and you will mention the x value over here. X would be equal to computers, and your y will be equal to computers, the target variable. The target variable here in this case is minutes. And just use them thing. Okay, so once you do this thing, you will try to fit the model. So to create the to fit the model, you will first create an object of this linear regression class. So you'll say linear regression, create an object of this. Okay, and then using the model, you will fit x and y. Okay, and then so obviously if you execute this thing, you won't see the result. So to see the result, you will say print me the intercept. I will say model dot intercept underscore, and I'll say print me again the slope. I'll say model dot coefficient, and it will give you exactly the same value what we had derived from using calculus over here. As you can see, the exact 4.16 and 15.50. You don't have to do calculus anymore. You just have to simply import this library and use it. That's it. It's just a tool that you'll be using it. I hope this makes sense to you. So if you were to ask me how to plot this, it's pretty simple. So I will say best fit model. Best fit model is equal to my the intercept, right? So I will say intercept. Sorry, y mx plus c, right? So I will say model dot coefficient underscore into the x value. X value was computers units plus the intercept. Intercept would be model dot dot intercept underscore. Okay, and then I will create a as computers. Sorry, I'll say computers. A new column known as best fit is equal to best fit model, and I will just say computers. These are the appropriate value, and to plot it, it's pretty simple. I will simply say figure comma axis is equal to figure dot subplot ax dot scatter. X is equal to units, and your y is equal to the minutes. Your data is equal to computers. And I'll say x dot plot. I want to plot a straight line, so I will say computers. So hang on. Computers units. Computers. I will say best fit. The column that I've created, this column, best fit, and then I'll say the color should be red. Okay, so here the color should be blue. I'll do that as well. Should be blue, and I will say ax dot set y label as minutes. I'll say ax dot set the x label as units. I'll say ax dot set title. I want to mention the title as well, so I'll say test fit model. Okay, there's an error somewhere. Access plot. Oh, I'm sorry. It should be plt.subplots. Now what is the problem? Oh, spelling mistake. Computers here, spelling mistake. I'm sorry. Okay, now it's fine. So this is the same value that I'm getting that I had if I had used the calculus, but I don't have to use calculus anymore. Okay, so this is a simple example of a linear regression model that I had explained to you. So before we go any further, is there any doubts or any questions so far that you may want to ask me? Anyone? Any questions? So were you able to understand everything? That is my question. Like, yeah, you can speak up if you want.
Well, actually, I had doubt half an hour back, but due to an English class, I had to leave the annotations part.
Okay,
Like,
which
I
good.
did not understand the code actually.
No problem. Which code are you talking about? Are you
At the
talking about
beginning, right at the beginning, where you first wrote annotations.
here, this part?
Yes.
Oh, it's pretty simple, man. It's pretty simple. So annotation literally means to decorate something. Okay, you are using annotations to decorate your graph. Now, when I say decorate, it should be meaningful decoration. So basically what you're saying is that if you had not done this part, okay, it will look something like this thing. Now you want to decorate it. Basically, in other words, you want to tell the users that this red line means mean value, like mean repair time, whatever it is, mean repair time. This is what you want to decorate it with, and you are using annotations for decoration part. Now here, what I did was, so to do that, you will call a function known as annotate, and you will mention like what is it that you want to write. You can write anything, mean repair time, a bin, anything you can write. And here you will give the x and y value from where it should start writing it. So I have given the x value, like I'm saying that obviously it should not start writing over here. It should start writing over somewhere from here. So clearly I can say that it's like the coordinates. You give the x coordinate over here. So you will say the x coordinate over here could be, let's say 7.5. Let's say it is 7. Let's say this is 7.5. And this seems to be good place from where it should start writing. This is the x coordinate. So x coordinate is fixed, as you can see. But I still have to give the y coordinate. Y coordinate will be, I want to write it just above the 97.2 that I've given. So I will say y is equal, this line is 97.2. I will say whatever it is, I will say 97.2 plus a bit above that. It could be plus 2, plus 3, whatever it is. That's what I've given over here. So in the code, this is the place that I've given over here. So if you were to execute this thing, it will give you this part. Now, if you want this mean repair time to be placed here, you, instead of giving the x, you will change the x coordinate. Simple. So you will say, let's say you want to place it at 1.5 or 1. You will say 1. If you would do that, it will give you something like this thing.
Yes, I got it.
Got it? Okay, perfect. Anyone? Any question? Were you able to understand the concept behind simple linear regression? Let me see. If you have any doubt, you can speak up. Thank you. I guess it was custom, right? Not very sure. Anyway, so folks, were you able to follow me? So as you can see, data science requires some math, and when I say some math, like a decent amount of math, and some decent coding as well. So in the code that I've shown you, there was nothing to, I believe there was nothing to, to like, if you have been doing competitive programming, there was nothing that you couldn't have understood. Like there is no user data structure that I'm using. These data structures, like which is known as data frame, I'm not creating them. it is already written in pandas. I'm just using them off the shelf tools. So any questions? Like, shall we go ahead, or are you tired? We've been talking for 1 hour. Like, do you have some suggestion? Like, should we take a 2-minute break, 5-minute break, or shall we continue all the way till 3? It's up to you, folks. Do you need a 10-minute break? Because I just have to cover one more thing known as multiple linear regression, and then we can wrap up the day. Then we'll tomorrow look at one classification algorithm and one clustering algorithm. So, folks, what do you say? Should we take a 5-minute, 10-minute break? Rajiv says to continue. All right, so let's continue then. Okay, so here I had talked to you about a simple linear regression in 2 variables. Like there, we had only 2 variables, x and y. In other words, what if there are more than one predictive variable that will determine your target? In other words, like in my earlier example of housing prediction, I had told that size was the thing that was giving you. For example, as the size increases, I was able to predict the price of the house. Right? It was something like this thing. Okay, this means the predictor variable was, as you can see over here, the predicted variable was the size, and the target was the price. But we know for a fact that in the real world, only size of the house does not predict the price. There are other factors as well. So predictor variables could be size, could be number of bedrooms, could be neighborhood, could be number of, I don't know, washrooms, etc. So this is an example of multivariate linear regression. In other words, there are multiple variables over here. Earlier we had only a single predictor variables, but what if we had 2 of them? So let's step up the game a bit. So if you were to plot that, it will form a 3D graph. So in the 2D one, it was a line that was used as the model over here. So there was a line that would be used over here. So can you guess what would be used in a 3D one? In case of like, there would be literally a 3D with 3-dimensional visualization. So what would be the thing that would be used as the model? Can anyone guess? Let me see the answers in the chat window. Again, for example, I'm asking you to guess. Like, it could be wrong, right? I just want you to engage, that's all. Okay. A plane. Yeah, cool. Exactly. And hyperplane. A hyperplane would be used. So to save the time, I took the liberty to type the code before the session, and the plane will look something like this thing. I will go to the data set, don't worry about it. So the plane will look something like this thing. Okay, in hyperplane. Now let me tell you how this thing works. Let's take an example of multivariate linear regression. Okay, so I just wanted to show you how it may look like. So let me scroll all the way to at the bottom. So I will type I will say multiple, or let's say I will say multivariate linear regression. So let me explain to you that scenario. Let me show you the data set first. The data set that we're going to use for this is delivery data set. So where is it? Delivery. Yeah, this data set. So it's again a very short data set. This data set says the amount, the time it takes for the delivery person, your valet, to deliver the product will depend on the distance of the shop between your house and the shop itself, and the number of products. So we can say, like, as the number of products increase, the time taken to collect them will also increase. So that's why delivery time will increase. And also, as the distance increases, the delivery time will also increase. In other words, the number of product and the distance together will tell you will help you to predict the delivery time. So this is the data that you can see. So to deliver 7 products, and let's say to cover 560 meters, it takes about 16.68 minutes for the delivery person. So the job at hand is to create a regression model which can do this prediction. Right. So again, I will all the necessary libraries have been imported already. So I will create a data set known as, let me zoom in a bit. I will create the data sets. I'll say read the data from the data set reading the data. I will say that. Hang on. Reading the data. I will say delivery is equal to pd dot read csv. I will give the path. Tell that the path is delivery dot csv file. Okay. And if you were to view the delivery dot head, it'll give you the data frame, something like that. So there are 3 columns, and then so this head gives you the top 5 rows. So if you want the top 10 rows, you can write head slash so inside the head function, you can give the number of rows that you want to see. If you want to see the last 5 rows, so by default it will give you 5-1. So if you want to see the last 5, you have to give delivery tail. This would mean there are 24 indices. That means there are 25 rows total, because the index starts from 0. So from 0 to 24 means 25 rows will be there. Okay. Let me change this back to head. So 0 all the way to 24. Perfect. So before doing some feature engineering, let's try to find out a bit about the columns. So if you want to give a basic insight into our columns and the data types of column, you will simply say delivery dot info function. It will give you the data type of each column and how many non-null values are there. In other words, how many missing values are there. Turns out there are total 25 rows. So as you can, there are 25 entries, 0 to 24. And each of them contains 25 non-null values. That means there are no null values. There is no missing value. And the data type of the first column is int. Second one is also integers. Third one is float. So, okay. Now, if you want to get some statistical insight, you will simply say delivery dot describe function. It will give you all the statistical values over here. So the describe function will give you the mean value of all the columns of each numerical column, the count value, standard deviation, minimum and maximum, and the first quartile, third quartile, and the median value as well. So the median value is 7 in number of production. So once you put them in ascending order. Okay, perfect. And again, if you want to visualize the data, you will have to use something known as Seaborn library. Again, Seaborn library is another library built on top of Matplotlib. It provides some additional functionalities. So I will import that. And I'll say sns.pairplot delivery. So hang on. Perfect. So what it tells you is that it gives you a pair plot. What in other words, it will give you a relationship between each column against each other. In other words, look at this thing. Okay, let's focus on this one. Okay, this one is the scatter plot between distance and number of product. So as you can see, as the number of product increases, the distance also increases. Okay, this one will be the plot between distance and delivery time. So as the delivery time as distance increases, the delivery time will also increase. Make sense? So this is the pair plot to find relationship between the pairs. So using the same technique that we had used before, if you were to find if you were to build a multiple linear regression, you will use something like this thing. You will say from sklearn.linear. You've already done that. Again, let me write it over here. You will say from sklearn.linear model import linear regression. And then I'll say I will create an object. I'll say model is equal to linear regression. Create an object of this class. Okay, and then I will select the predictor variables. So I will say the predictor variables should be equal to delivery. Inside the delivery, I have to give a list over here. Now the thing I have to tell you is that this, you can only enter one element inside the list. Okay, now if you were to enter like this thing, n number of products, n prod, comma, distance, there are two elements inside this list. So how to do this thing? It's pretty simple. Enclose this list inside another list. Okay, what this means is that this outer list will contain only one element. This outer list can only contain one element. Now this one element could be a list. What in other words is that, let me give you an example for an analogy. If you were to let's say if you want to buy some groceries from the market, and you take a list, you take a piece of paper and you write down some products that you want to buy. Could be eggs, tomatoes, potatoes. Let's say there are three items: eggs, tomatoes, and potatoes. And you wrote those three things in a piece of paper, which we'll call the list. And then you're walking down the road to the market. And then I meet you on the road, and then I ask you, hey, how many elements do you have in your hand? Your natural answer is going to be one. You hold only one piece of paper, or you hold only one list. Now inside that list there could be multiple items. That is different. So in your case, inside that list there are three items written: eggs, potatoes, and tomatoes. But if I were to ask you how many elements are you, like how many things are you holding in your hand, you will say only one element. That is a list, single list. Similarly, this single list is containing multiple items. That is allowed. But this outer list can only hold one. So the way to do that would be to just enclose the list, and enclose the element inside another list, so that the condition is met. Simple. Okay. Similarly, and we will create the target variable. Now the target variable is always going to be one. So that is why there is no need to have two lists enclosed, like two nested lists. There's no need for that. So you could simply say del time. Okay. And then here you're going to build the model. So building the model using fit function. Fit method, same thing. So you'll say model.fit, fit the x, comma y, and then print me the intercept. So in this case, there are going to be two intercepts. So I'll say print the intercept. Model.intercept underscore, and say print the slope. So there's only going to be one intercept, but the slope is going to be there are going to be multiple slopes. My bad. I'll say slopes, comma, a model dot coefficient. If I were to run the code, it will look something like this. Okay. As you can see from the image over here, so here the z-axis would be the target variable. So the number of product and the distance would be the predictors. This is x1, this is x, y, and this is z. So this z would be so there's only one value at z where this plane will cut it. Yeah, so that is why intercept is going to remain 1, but there will be two angles with which this hyperplane will make an angle with x axis and also with y axis. That is why slope is going to be 2. Anytime you have any doubt, you can always ask me. And if you were to visualize this model, you will type the code. You will say from mpl.toolkits mpl underscore toolkits dot mplot 3d import access 3d. You will create a canvas. Figure is equal to plt dot figure, and you will mention the fig size to be the figure to be 7,7, let's say. And then you're going to create an axis known as ax figure dot add subplots. Subplot, let's say 101. Projection is equal to 3D. X dot scatter. XS is equal to delivery dot prod y is equal to delivery distance zs is equal to delivery L time, and the color should be equal to blue. And here I'm going to set the x-axis. I'll say axis dot set label x label to be number of products. X dot set y label to be distance, and ax dot set z label to be build time. This is what you're going to get. So far you can see. So this means the dot which is darker in color, which it means it is closer to the user, and the dot which is lighter in color, it means it is farther away from the user. It's pretty simple. And then you will create the hyperplane. Now to create the hyperplane, it's a very, very, very big code. So I will just simply copy paste this thing. Okay. Now this is the idea behind a multiple linear regression model over here. So this is how your multiple linear regression is going to work. Now, obviously, if the number of predictor variables goes more than 2, you won't be able to visualize this thing, because we literally cannot visualize anything more than 3 dimension. That's literally not possible. So, however, the idea remains the same. That means we can have any n number of predictor variables. And although we cannot visualize them, we can validate the model by finding the sum of squared errors and everything. And even in this thing, we can validate the model using the score method, like how well it is doing. So if you were to validate this particular model, you can do that. You could say, like score method is used for regression model, and it returns the coefficient of determination value for the model. So it will simply say. We'll simply say print model dot what is the score and give the x and y value. It turns out the score is about 95.95%, like around 96%. It is accurate. Right. So I guess we can wrap up for today, because there are other variables as well. But I guess for the beginners, this would be enough. Now, from tomorrow, here we talked about regression values over here. Now, important thing before we leave, we have to understand regression is used for continuous data type. So when I say continuous data type, regression is used whenever the data type is continuous. In other words, if there is a value 1, 2, 3, okay, 4, so on and so forth, and here let's say 1, 2, 3, 4. What you have to understand is that there are infinite number of numbers between two real numbers. In other words, between 1 and 2, there are infinite possibilities, like 1.1, 1.2, like even between 1.1 and 1.2, there will be 1.01, 1.02, so on and so forth. So there are infinite possibilities. In other words, if you draw a line, something like this thing, there are infinite possible values over here between this value, between 1 and 2, between 1, hang on, let me change the color, between 1 and 2, there are infinite possibilities. That is why you will use regression. This is where regression is used. However, if there is a place where you want to use classes, where there are a finite number of objects, then you will use classification. So let me give you an example of classification. Let's say you want to build a machine learning model which will which will contain two classes. Let's say, in other words, this is a machine learning model, ML model. Okay, and then you will feed an image of a cat or a dog, and it can give you two values over here, either a cat or a dog. In other words, there are two classes in this case. There are no infinite value, there are no infinite possibilities. There are only two possibilities, and your machine learning model will pick like one from the two. Okay, in other words, this is known as classification type. So if I were to ask you, like, what if I create a machine learning model? Okay, this is a machine learning model, and I give an image of a number. Let's say this is the image of a number. How many total classes are possible? Can any of you answer me that? Let me see the comment section. So my question is, if I give a single digit, how many possible classes would be there? So in this example, I have defined there will be only two classes, either a cat or a dog. But if I give a digit, and if I were to, and my question is, and my problem at hand is digit recognize, we have to find a model so that it can identify the digit, or it can, recognize the digit. So there's an example, digit recognition. So how many total classes would be possible in this case? Classes 1. Yeah, the answer is 10 actually. How? Pretty simple. There are 10 possibilities. 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Total. The digit, if it's a single digit, it has to be like from these classes only. Okay, so this will be an example of 10 classes. However, the idea remains the same. There are finite number of outputs that are possible. But in case of regression, there are infinite possibilities. So this is an example of continuous data type. And this is an example of discrete data type. Discrete means distinct, which is finite and countable. So tomorrow we'll talk about them, and also unsupervised machine learning. So I'll give you an example of clustering where the data will not be labeled. You will use parameters to identify the patterns in the data. So I guess we can wrap up for today. Before we leave, any questions so far? Any question, comments, concerns, anything? Right, so before we actually leave, I also have a YouTube channel. So if you are interested in data structures, algorithms, and data science, you're welcome to subscribe to this YouTube channel. It will motivate me to make more videos. So this is the channel's link. You're welcome to subscribe. You're also welcome to follow, add me onto your LinkedIn. My LinkedIn profile is Abin Verghese. I will just, this is the link. So you're welcome to do that. Yeah, feel free to reach out to me anytime should you have any doubt. So we'll meet tomorrow. So with that being said, cheers. You want me to send the code? I will send the code. Okay. Okay. Reach out to the organizers of this event, and I will give the code to them, and probably they can send it to you. Okay. Or you know what? Reach out to me in LinkedIn on LinkedIn. Okay. I will send out the code there. Sounds good, Rajiv? Excuse me. Are we all good, Rajiv? And yeah, Rajiv, please call me Abin. I don't need sir. Yeah. By the way, in industry, we are asked to call even the CEO by their name. Right. Sounds good. So thank you all for joining in. I hope you had a good time, and we'll meet tomorrow. Cheers. Bye bye.